Hello everyone. My name is Shunping Huang, and I'm a Googler, and I am also the latest committer of the Beam Apache Beam project. So today I will be introducing the new transform called anomaly detection for simplifying the building of streaming anomaly detection pipelines. So picture this. So four friends got their exam result back, and the first three got 96, 100, and 94. The last one, who can see from his sad face, got 80. So although 80 is not bad score at all, right? But we can see it's a bit different from the other three numbers. And that is what we call an outlier or anomaly. So simply put, anomaly is a data point that is different from the norm. And anomaly detection is to find these outliers. And anomaly detection is useful in various scenarios, including in our above example, helping teachers to identify the best teaching strategy for different students based on score anomaly, and also allowing engineer to spot malfunctioning equipment based on, for example, sensor data's anomalies. And how, so the definition of anomaly actually depends on a few things. For example, what are the normals? So is that based on like average or based on like a majority? And also it depends on how we measure, for example, deviation. By distance, by density, or by other metrics. So this consideration leads to different kind of anomaly detection approaches, and anomaly are viewed differently across different data. And so from what data are we looking for anomaly? So these is the key questions everyone who wants to employ the anomaly detections to their pipeline need to ask themselves. So anomaly can exist in different type of data. For example, it can exist in the bounded data set, like the rise or dip of companies' quarterly sales figure. Or it can also exist in unbounded data, like the unusual patterns of network traffic. Anomaly can be univariate. In our above example, the outlier scores we've seen. And it can also be multivariate. For example, consider someone shooting arrows to a target, and if most of the arrows cluster in the middle around the bullseye, and one arrows are way far away from the middle, that is a spatial anomaly, which is represented by an XY coordinate. So if you think about the anomalies in time, like unbounded data. So usually unbounded data, we have a timestamp associated to it, right? So we further categorize this into two scenarios, actually two types. In the first type, and we assume that the data points are independent and independent and identically distributed, which we also call IID. So you can see the picture on the left. So basically, so we assume that the data is drawing from the same distribution, and if there is some global, there's a big deviation from that distribution, that we will consider as an anomaly. And another type is shown on the right. So in this case, the data points have time dependent. So, for example, think about like the number of the number of taxi rides in the New York City. So you can see there is some kind of like a seasonal patterns, and a sudden increase of the number of taxi rides may suggest, like, for example, a rainy day. So finally, for data streams, some of them may exhibit like something called the concept drift, where the underlying data distribution change over time. So that's what you see in the third picture. And as shown there, the distribution shift in the midstream, and then it shifts back to the normal. So this can happen, for example, a sensor goes normal for a period of time, and suddenly it goes bad. And then after a period of time, or after recalibration, so it jumps back to normal. So in this case, we will be very interested in finding those change points, and also we want the model to adapt to the model change, so that you will not fire the anomaly for the period when the distribution is changed. So to facilitate users incorporating the anomaly detection logics into their pipelines, we implement the new p-transform called anomaly detection. And so as one of the latest ML transforms, so user can easily use that by specifying detectors and apply their p-transform on the apply their p collections on the p-transform. And let's consider the whole p-transform as a black box and take a look at what's the input and output. Each element of the input is a keyed beam row. So remember, a beam row is a beam type which is kind of like a tuple-like immutable type, and we use that to store data in a portable way. The output element is also a key value pair. The key is the same as the input, and the value is actually a data class called anomaly result. Inside the anomaly result, so we can see like we include the original data, which is we call it example, and also we have a list of predictions, which is the place that we store the prediction result. So we will have a list of predictions because you can apply like multiple detectors or detection algorithms on the same data and get the result. And inside each of the anomaly prediction data class, you can see like we have a model ID, we have the outlier score, which I use the yellow to show it, and we also have threshold, which is the cutoff we use to determine whether it is an outlier or not. And last, we will have the label. So 0 means normal and 1 means abnormal. And so this is the output. Okay. So let's jump a little bit further to look inside of what anomaly detection p-transform works. So at the core, we have individual detectors. So these individual detectors actually runs a specific anomaly detection methods and generate scores or labels. So currently we have implemented some statistical method like incremental z-score or interquartile range. And also we support like offline models such as isolation forest. LOF is the local outlier factor, and also one class SVM, etc. Those models are actually supported by the PyOD, which is a very popular outlier detection Python library. And each individual detectors can have optionally a subcomponent called a threshold criteria. So we found the threshold criteria, which is the picture shown on the left. So the detector will get the incoming data, and then it will get a score as the output. And if there is a threshold criteria specified, we will apply this threshold criteria on the score, and eventually we will generate a label. For example, we can say, okay, we have a threshold to be 3, then anything that more than 3, then it will be we will label as like 1, which is outlier. Beam right now support like 2 different type of threshold criteria. The fixed thresholding, which we use, of course, a fixed threshold a fixed cutoff, and then a quantile thresholding, which we use a quantile as the threshold. For example, you can say 95th quantile as the threshold. So everything that is above the 95th quantile, you will say that's an outlier. And to build upon individual detectors, we also have like ensemble detectors. And in the ensemble detectors, we run a set of sub-detectors in parallel and aggregate the scores or scores or labels back. And notice that these sub-detectors can also be ensemble detectors. That means that you can use this whole framework to build like ensembles of ensembles in a sector. The specific aggregations logic is determined by the aggregation strategies, and so it's also a subcomponent for these ensemble detectors. And we have two types of aggregation strategy, one for the scoring and one for the labels. So for scoring, definitely you can say you want to take the average of all the scores generated by the subdetectors, take the max of all the scores. And for labels, we can say, okay, I have a bunch of labels from the subdetector. Some say yes and some say no, and then we can have a mechanism to vote whether this is an outlier or not, based on, for some majority vote, or we have, if any one vote is outlier, we can say this is outlier, something like that. And so there are actually three usage patterns for these ensemble detectors. So I have shown it into the three small pictures here. In the first picture, so I want to show the case that the subdetectors are homogeneous, meaning that all the subdetectors are running on the same method, which means that combining their scores output is very meaningful. So that's why we will have a score aggregation here. And in the second scenario, if what we want to get is like the final labels, and so we can actually add the threshold criteria under the second scenario to get the label. And in the third scenario, we are looking at this case that the subdetectors are different. So in this case, if the subdetectors are different, meaning that they are different methods, and the scores they generated is like totally of different scales. So in this case, it doesn't make sense to calculate the average of those scores or merge those scores together. And in this case, what we will do is that we first generate the labels for each of the subdetectors, okay, and then we have a label aggregation to say take the majority vote, take all the vote, in order to generate the final label. Let me switch to my demo. Okay, in this demo, I'm using a Jupyter Notebook to show like how we use the anomaly detection p-transform on both batch and streaming data. And the detector I use is basically just the z-score detectors, but you can change the detectors to use the other ones. And so first is kind of like the setup, and I skip those parts, and so that we don't need to wait for that. And let's start here. And I first generate the data, which is like I just randomly sample the data from a normal distribution and also add some outliers there. And yeah, so this is the picture of the data, the input data. So you can see that the data is here, and then you can see some outliers. And we have a Beam pipeline here to run on this batch data. And remember, we have the anomaly detection p-transform here, and we specify like z-score as the detector. And so to run it, and then it generates like so the outliers it detect here. Yeah, so I think it's this one and this one. Okay, and so in the second part, I actually extend the data generation to generate the data with concept drift. So in this case, I'm actually manually changing the distribution of the data from time to time. And so the data I generate looks like this. So you can see. So at first it's in the distribution, and then later we suddenly switch to the another distribution, and there's another distribution here, and there's another distribution here. Okay, and to run this model, I actually use a PubSub. So I actually create a PubSub topics, and then I publish this data set to this PubSub topic. And in the pipeline, I have a subscriber to subscribe to this PubSub topic and then get the data. So let me start the PubSub. Hopefully it works. Okay, perfect. Yeah, I create those PubSub topics, and then now I'm going to publish the input to the PubSub. Yep. And then I'm going to launch a Beam pipeline. So this Beam pipeline will run in the background, and I have another code here which will start to listen to the output PubSub and collect the output and draw it and bring it out to the Jupyter notebook. So this is the code that I use to collect the output, and then let's check how many outputs do we have right now. So we got 20 here. Let it stream. Oh, it's already got like 131. So next I'm going to just try to draw out what's the outcome of this the output. So okay, so it's going to draw out like a picture every, I think, 20 seconds or something. Yeah, 20 seconds. So yeah, while we are waiting, I'm trying to explain, like, so here we find the an outlier here, which is denoted as the red. So the green one are the normal point, and this red one is the outliers. So after 20 seconds, it's start to draw another part of the picture, which showing that we are actually streaming more data inside this pipeline. And you can see that we detect like outliers at the beginning of the shift. And after that, so this kind of like dot, even though they are at the same level as the previous dot here, right? So they are not classified as the outliers. So basically, our models try to adapt the change of the distribution so that it's not going to keep firing of outliers. And this is also what we call, like, we try to handle like concept drift in this case. Okay. And yeah, we have more data coming in, and so you can see like, yeah, so this is another outlier that we find. Yeah, and so on. Okay, yeah, that's the event. Eventually, that will be the final result of all the data points if we stream all the data points into the pipeline. All right, we can switch back to the main deck. So there are a couple of upcoming features for the anomaly detection. So given the current growing interest of YAML, so we are actually adding the capability of like calling anomaly detections via Beam YAML. I'm sorry. And so here you can see the example. So we can specify like the transform type to be anomaly detection, and then we define the detectors over there using a YAML format, and then we will be able to call the anomaly detection. And this feature is already released in the latest Beam 2.66 release. So the next exciting features we are trying to do is about anomaly detection on time series. And so basically the input of this, previously we are talking about data streams, and remember the difference between data streams and time series, right? And right now, if we are doing anomaly detection on time series, the input will be like a p collection of values from this time series. And remember that the input could be unordered. And in this case, what we are going to do is that we are going to first buffer the time series values and order them by timestamp, right? And then we, during that steps, probably there will be some gap or missing values in the middle. And in this case, we will have a step to fill those gaps. And finally, so we will apply time series anomaly detectors on the clean data, I mean a window of data, and then to get the final output outliers. And we have a very successful result from using Times FM, which is a foundation model for time series forecasting. And we use that for anomaly detection, and we got a very good result. And it's also worth noting that, so this is actually an intern project I have this summer in collaboration with my summer intern, Ashok Devary, who is also here. So thanks for joining Google this summer to help with this project. And if you guys haven't met Ashok, so come to talk to him after the meeting. So a brilliant young man from UC Berkeley, right? So these are the useful links. So the design doc, the source code, and then some Python doc, and the Colab I just run. And also there is another Colab for running isolation forest using the p-transform. So feel free to play around with. And we also encourage people to continue to contribute to it. So if you have any ideas, come to talk to me, or contribute to the Beam repo. So we are really welcome people to contribute to that. And that's it.